Hi everyone, and welcome to this Copernicus Marine Service training for ocean color. My name is Silvia Pardo. I am an Earth observation scientist at the Plymouth Marine Laboratory in Plymouth, United Kingdom, and I'm here today to help you explore some of the ocean color products you can access through the Copernicus Marine Service. This is part 2 of a 3-part series in ocean color, so please feel free to go back to part 1 if you need a refresher on data structure, how to open, load, extract, and plot in the data. Quick reminder that we are going to use this Jupyter Notebook platform. So to execute a cell, you just press the play button, and to stop the execution, you can interrupt the execution using the stop button. During the session, we will use Copernicus data to study the intensity and location, and to some extent the duration of and timing of a phytoplankton bloom. We will learn how to tell if a bloom is really a bloom or just a regional feature, and we will also learn how to extract an average data to build a time series for daily and monthly chlorophyll for the region, and we will use that to study the seasonal cycle of phytoplankton. Phytoplankton, as you know, respond to changes in the physical environment, and in the northwest shelf seas, the changes present a distinct seasonality. But we also have phytoplankton blooms that can occur when something happens that changes the chemistry of the ocean, such as freshwater inputs from melting ice and river runoff. And here we have a spectacular example of how nutrient increase can affect the color of the water in this image, acquired on the 16th of May by NASA's satellite Landsat 8, showing how this large plume of sediment that was originating in the eastern English coast and is traveling northeast through the area and is triggering blooms on this way, such as this massive one in the North Sea. As we did in part 1, we will begin by setting up the environment. Most of these functions we already use, but there are some of them that we are going to use, we either didn't use on part 1 or we were going to use them in more detail in here. So first we have the string module in here, and in this exercise we will use it to define a string template and to perform a simple string substitution. For example, we will create a template for the file name of monthly products in the Atlantic region. And most of the file names, as you know, are fixed for center products, and we can define a template that leaves some parts of the file name fixed and defines placeholders for the variable bits, such as the date, for example. Then we will have the globe module, which is very useful when used in conjunction with the string module and the templates, and this will allow us to identify and list file names with a file name matching a certain pattern or we'll define with a template. And last but not least, we have the math module, which is probably self-explanatory and allows us to perform high precision mathematical operations. As we did in part 1, we will need to tell the system where to find the data. So we have the usual definitions for the data root directory, data directory, and results directory. And remember that all the data for this exercise has already been uploaded to the platform, but if you're using your own data in your own computer, you will need to define new variables pointing to the right place. The datasets that we are going to use for this exercise are quite similar to the ones that we used for part 1. So that's the Atlantic chlorophyll reprocessed dataset at levels 3 and 4. So what we have in here is a list of daily files acquired over the North Sea at the beginning of May 2018, when we know a phytoplankton bloom was taking place. And I have just shown you an image of the same phytoplume later that month. As always, we define a path that tells the system where the data is, and then we can start loading the files and accessing the data inside them. So for this, we will, as we did in part 1, we will use the X-array module and within the module, the open dataset function. And this is probably a good time to mention that we are using the simplest possible argument configuration when we call open datasets. But the function actually has a lot of options, such as this option called drop variables that stops a subset of variables being loaded, which might be quite useful if you have a dataset that contains a lot of variables and takes a lot of time to load. Because we don't have a lot of time in here, we won't be able to chase the chlorophyll blooms for this particular region for days and days. So we are going to cheat a little bit, and I will tell you that the 6th of May was one of the days where the bloom was more intense. So we are going to have a first look at the chlorophyll at that date. And in here we have extracted the chlorophyll latitude and longitude variables from the CCI chlorophyll level 3 daily 6th of May dataset, and assign them to the corresponding variables that we will use for plotting. We will not create a chlorophyll map for the day. So as usual, we initialize a figure and a certain size and resolution. We will create an empty map, and we will add the coastlines as defined in here, and we will plot up using the p-color-mes function to create a pseudo-color map. Some formatting in place. We will use the grid lines to define grid lines until our plotted that the grid lines will be labeled. Remember that all the labels are present to begin with, but we can override this behavior by deleting, for example, in here, the top and the right hand variables. Then the style of the labels are configured as usual, so we can specify the rotation and the size and the color. And last but not least, we will use the color bar to help interpret the data. So that shows the relationship between the actual values of chlorophyll concentration and the colors we can see in the map. If you compare this plotting exercise in here with the ones that we use, plotting sequence we will use in part 1, you will see that probably the only difference, well, there's two main differences. The first one is that we are defining a second projection in here called Mercator. So we want to plot in Mercator because the projection is more realistic in terms of distances for this latitude. You might remember that the British Isles, when we zoomed in the British Isles at the end of part 1, they look a little bit flattened, so the image was a bit distorted. But the grid line function in here only allows us to plot using this projection basically. So what we're gonna do, and we will be continue to do in the exercise, is to define the projection we want to use, and also the projection where the grid lines are supported, and we will use them in conjunction as a little trick to as you can see here. So in here we are defining the plot in Mercator, but then to do the actual plot we will do a transformation to Plat Carré to have the grid lines working. The second difference is that we are defining the geographical extent of the map a little bit different. So as you can see in here, in these lines, basically, we are specifying a maximum and minimum for the X and Y axis. And obviously, this has an immediate advantage. We don't have to go through the hassle of slicing as we did in part 1. So this is fantastic for visualization, but obviously if you're going to do any type of statistical analysis, then you will have to probably extract the subarray you want to use to perform your statistical analysis using this slicing technique. So with all this, we have our chlorophyll concentration map for the 6th of May 2018. If you've never seen phytoplankton bloom, you might be surprised how much structure you have in that image. We have some irregular shaped gaps that correspond to cloud cover, but the most striking striking things are these vortex-like structures, which are called eddies. And as you know, there are major current systems across the ocean, and in particular in this region. And this happen when large masses of water spin off these current systems, forming like a whirlpool kind of pattern. And they can be massive and be quite persistent, and they can travel a really long distance from the place they were originated. Eddies provide quite a nice example of the synergy between the biogeochemical variables available in the Copernicus catalog. So in here, I have set up a little challenge. So I suggest that you create a salinity or sea surface temperature. So probably sea surface temperature is easier to start with. And you create a map for exactly the same date and region, and see if the structures you can see in there match the structures and the eddies that we can see on the chlorophyll map. So now that we have all visualized our bloom, we can ask ourselves how the bloom changed from day to day. Conveniently already have it. We have already identified the list of files around the 6th of May 2018, and we can straight away visualize them. We have using here a new plotting function called Subplot, as you can see in here, to visualize a range of data in the same subplot, as you will see in a minute. So Subplot is part of the Matplotlib Matplotlib library. So each one of these instances of the subplot function add a subplot to the current figure. So the important thing when calling this function is to know how to specify the position of the subplot within the big figure. So here we have used one of the possible options and provided 3 integers that represent the number of rows, the number of columns, and an absolute integer. So in here we have a figure composed by 4 subplots, so that's 2 rows and 2 columns, and this subplot in here is the first one of the 4. And as you can see here, the second subplot, again 2 rows, 2 columns, second subplot, third subplot, and fourth subplot. Within each one of these subplots, we use exactly the same plotting sequence we use for part 1, and for creating the daily chlorophyll map we have just generated. Because the geography is the same for the file, we don't need to waste processing time redefining the coordinate grid every time we add that subplot. So in fact, we are reusing the daily to the long and lat variables that we defined for the daily file. And we don't need to visualize all the dates to get an idea of how the bloom changed from day to day. So in here we have chosen 4 dates, but you can add further subplots to the code box to see the complete sequence if you are interested. As you can see, the intensity and the location of the bloom can change quite a lot from day to day. In particular, we have persistent currents that are picking the water as they go. For example, in here we have a current of high chlorophyll concentration that probably has dissipated or joined and formed these 2 blobs in here, these 2 blobs of high concentration chlorophyll 2 days after or 5 days after the plume was originated in the first place. Again, for this exercise, you can identify the salinity and sea surface temperature for these dates and see if the structures match. So with this, we have a visual footprint of the phytoplankton bloom and a general idea of how it evolved with time. So obviously the next question is, can we pinpoint the exact extent of the phytoplankton bloom on the map? And obviously there are several ways to do this. The easiest ways will be to compare the values in their map to a predefined number. So for example, going back to our initial map for the 6th of May, we can decide that every pixel with concentrations above 1, so that's this turquoise blue color, we can decide that everything above that is part of a phytoplankton bloom with color-free concentrations above 1 milligram per cubic meter. The problem is that that threshold depends a lot on when and where we are looking at. So, for example, something that works in the North Sea in spring in here will be useless for the Baltic Sea in the summer. In the summer, the Baltic Sea's mean concentrations of 3 milligrams per cubic meter. So if, as we suggested, we use 1 milligram per cubic meter as the threshold to detect blooms in the Baltic Sea during the summer, the whole region will be flagged as an active bloom. So for this reason, it's better to calculate the threshold taking into account all the information available in the map using statistics, in particular statistical metrics such as the regional mean and median. So this is exactly what we are going to do in this new step and this new box in here. So to calculate the median and the mean, we use the NumPy, non-median and non-mean functions. So these are probably self-explanatory, but they take into account that some of the elements of the array can be masked, can be not a number, so none, and they basically ignore them when they calculate the mean and the median. So if your data array is completely empty, the function might throw a warning, then that's why one of the reasons why we set up our environment to ignore warnings. And so we have then printed the median and the mean of the chlorophyll. You can see that the values are the same order of magnitude, and this is to be expected. So, because if we go back to the regional map, we see that most of the region is covered by offshore waters with typical chlorophyll concentrations around 1-2 milligrams per cubic meter, and those values are driving the resulting mean and the median values. So we will use these numbers as thresholds to study the extent of the bloom. In particular, we will see what happens when I use the mean chlorophyll, and then you can test the same kind of approach using the median instead and see what the differences are. So we first select the pixels that belong to the bloom using this threshold. So that's exactly what we are doing in here using the NumPy function where. Then we have, so this is exactly the same function that we use to zoom into a region in the map and then to extract a box corresponding to a certain coordinate limits in part 1. There we had multiple logical conditions, and here the logical comparisons is performed over the daily chlorophyll value. So we don't need to perform any transformation on the resulting indexes as we did for the latitude and longitude. Then we create an empty array, and that has the same shape as the daily chlorophyll variable, and we fill it with zeros using the NumPy zeros function. Then in a very basic way, we flag the pixels that belong to the bloom, so those that correspond with positions in the map that are defined by the bloom indexes, and we manually change the value of those specific locations to 1, from 0 to 1. And finally, we can plot the extent of the bloom, exactly the same sequence, but we use color mesh. And because we are only trying to flag which pixels belong to the bloom and which pixels doesn't, the color map array only has 2 values, so using a full color map makes no sense. Instead, we have built our own using 2 colors. So we have white for pixels that do not belong to the bloom, and green for pixels that belong to the bloom. So we define the custom color mapping here, and then we will use it within the p-color-mesh, the pseudo color mesh function. So that's what the resulting image, resulting map looks like. As an exercise, as I said, you can replicate this using the median instead of the mean as a threshold, and see how this map changes. So as you can see, that decisions that lead to this threshold are quite delicate. So the areas that we are identifying as blooms are quite large, and this again might be surprising. It might change with a different threshold. For example, if we calculate this mean and median values for the whole Atlantic, both values will be much lower, and you will end up with a lower threshold. So that means that most of this area will be flagged as a bloom, because the North Sea has typically higher concentrations that the Atlantic or North Atlantic seem as a whole. So this also can lead to false detections. So whether it's frequent to see high chlorophyll values along the coast on these areas. This can be there for basically all year long. That doesn't mean that it's a transient bloom. So what we're gonna do next is to try to assess if this bloom map is realistic. To fix this problem that we might have of false detection, we need a way to decide if a value is normal or anomalous for a specific location. Again, there are different techniques to do that, but we are going to use the quickest and probably most efficient way, which is constructing a climatology. So a climatology is kind of a baseline, a reference that describes what's the typical status of a biogeochemical variable, in this case chlorophyll. Then we can measure the anomalous character of the values by subtracting the reference value, the climatology, from the observations. In the case of chlorophyll anomalies, this is done on a pixel by pixel basis and usually in log space, but it doesn't really affect the final result that much for this exercise. Different temporal time windows can be chosen depending on the application. So, for example, we can do an annual climatology where we effectively are removing the seasonal signal, or we can do a daily climatology, as we will do in the next box of code, which provides a measure of the typical annual cycle and can still be used to derive daily anomaly time series that reveal changes in the timing and the amplitude of the seasonal peaks. So what we are going to do now is to construct, as I said, a daily climatology for the 6th of May, and we will begin by listing the files corresponding to that day of the year for the 8 previous years to our bloom. So that's 6th of May from 2010 to 2017. Then we load the data using the usual combination of open dataset and variable assignment. And then we extract the daily chlorophyll array for each one of the days, and we end up having a list of 8 daily chlorophyll arrays, 1 per year, and we need to put all the data together to facilitate the averaging, the climatology computation. So to do this, we define a list object called daily chlorophyll list for the 6th of May, containing all the different data arrays. We then stack the arrays, so we go from a list of 8 two-dimensional arrays to a single 3-dimensional array, where the 3rd dimension is built by pasting the 2-dimensional arrays one after the other. So by stacking, we are basically adding a 3rd dimension, which in this case is a temporal dimension. Then we will use that temporal dimension to calculate the temporal average. And we do this using the Numpy Stack function. So it takes 2 arguments, the list of variables that we have just defined, and the access for the new dimension. So remember that indices in Python start at 0, so an index labeled as 2 is actually a 3rd axis, or a 3rd dimension. And finally, we calculate the 8-year daily climatology by using, again, the Numpy, not the number, mean function that we used above to create the thresholds for the daily chlorophyll. We have used this function before, but basically in a different way. Because we didn't have to, we were doing a regional average, and we didn't have to indicate which axis the average was going to be performed. And in this case, because we have a 3-dimensional array and we don't have to average in all the dimensions, just the time, we specify that by using axis equal to when we call the function. And we store the climatology in this variable here called daily chlorophyll climatology 6th of May, that we can now use to plot the climatology map using exactly the same sequence that we have used to create the daily map for the 6th of May 2018 that we just seen. As you can see here, this is the resulting climatology map for the 6th of May, aggregating 8 years worth of data. And that clearly increases the coverage and decreases the variability. So see in comparison the daily snapshot for the same date for the single year, you can see that the big blooms that we detected for 2018 are not present as one will expect in the climatology. And we already saw this effect when we compare level 3 and level 4 products in part 1. So the results over the coastal areas are quite revealing. Most of the coast and the northern border of the English Channel seems to have sustained high chlorophyll values in the 8 years previous to the date of interest. So in other words, concentrations above 5 milligrams per cubic meter are normal for this region, and doesn't necessarily imply that we are looking at a transient phytoplankton bloom. And now we can put this chlorophyll climatology that we generated and visualized here to good use to derive the chlorophyll anomaly. To do this, we only need to subtract our reference daily climatology for the daily chlorophyll mean values on a pixel by pixel basis. And that's exactly what we do. And this subtraction here is literally just subtracting from array to the other. And we store the resultant anomaly in this variable and we plot it, and basically this will help us decide if some of the high chlorophyll values for 2018 represent a bloom or not. So basically we plotted using again the same sequence, exactly the same formatting we have been using for the past half of the part 2 exercise. The only difference is that we use blue, white and red color map to make the positive and negative anomalies more evident. So this is what we call a divergent color map. So that means that divergent color maps have two major color components, in this case blue and red, and the map transitions from one color to another, passing through an unsaturated color, which is white in this particular case. So the areas in blue mean that the daily average values for the 6th of May 2018 were lower than the climatological value, and the red areas mean the opposite, that the daily average values for the same date were higher. The anomaly map reveals that for this date and region, the most anomaly values are actually found along the coast, as we know. This is probably a surprising result, considering that we already saw that the chlorophyll values were quite high to start with in the climatology, but basically this means that this is a bloom happening in 2018, and it's the same with the two regions or the three regions that we saw at the beginning. Whether the English Channel is experiencing the opposite of a bloom, so chlorophyll for 2018 is actually lower than the norm. So to finish this part 2 exercise, we will put together a range of time series of chlorophyll concentration to gain some understanding about the phytoplankton seasonal cycle. And as with anomalies, time series can be assembled at different temporal and spatial resolutions. And we have now seen several times that temporal aggregation increases the coverage, the amount of data available, but it has a smoothing effect which might lead to information loss of strong events. If we talk about spatial aggregation instead of temporal aggregation, we have to bear in mind that the data can be extracted at particular locations or for standard regions. We are going to be using a standard region, and that means that regional mean values will be calculated by performing the average, weighted by pixel area if needed, over the region of interest. So first in here, probably quick reminder of how to extract the spatial subset of the data. So our area of interest will be the coastal and shelf region of the Celtic Sea for this seasonal cycle study. And here we have defined the bounding box for the coordinate box that surrounds this area. We will start looking at the situation for the 26th of March 2019. And here we are basically defining the file and loading the chlorophyll variable for that date. Then we will use the Numpy function to identify which pixels are inside the geolocated box that we have just defined and which pixels are outside. Remember that we use Numpy squeeze to convert back from two-dimensional index arrays to one-dimensional index array. And last but not least, we extract the zoomed in data from the original daily data by replacing the columns we have initially at the beginning of this practical session by the actual latitude and longitude subset indexes. And in here we have plotted the zoomed in area, same plotting sequence as always, a slightly different color map, but the main important thing is that you can see how we are zooming in into the Celtic Sea for the 26th of March 2019. So previously, when we wanted to study the same product for different dates, we would just define a long list of dates as we did when we studied the phytoplankton bloom across the beginning of May 2018, I think it was. Obviously, the longer the time series or the longer the time period you want to study, the more tedious this process is. So we are gonna learn how to shortcut this process of having to write all the file names. So to do this, we will use a Python control structure called a for loop that you can see in here, which is used to iterate over a sequence. In this particular case, we will take it to iterate through a list of numbers that will represent the different months of the year. So that's month 1 to 12. So 13 is the upper limit of the range. So what are the statements that we are going to put inside the loop? So as I said, we are going to try to build first a monthly time series. So we will use this loop to create a file list of monthly files for 2019. And from them, we will extract the time series data. So we have in here initialized a monthly file variable that will host the list of files, and we also are defining a twin list for the monthly dates. We will come in handy when we are plotting at the time series. So how do we identify the monthly files that need to be added to the monthly file list? For that, we need to scroll up a little bit and look at this, where we have defined a reference pattern for monthly file names by making use of Python string template. Python allows us to define string templates with two types of components. So we have fixed bits, like this bit over here, and variable bits that are represented by variable names inside curly brackets that are preceded by the dollar symbol, as you can see. So basically what we are defining here are file names for monthly files where the year and the month are variable, and that will allows us to loop over all the month files for a certain year, as we will see now. So going back to the loop, it will be executed from month value from 1 to 3 up to 12, as I said, for each numerical value of the variable m. which increases every iteration, and we then define the cumulative strength, a string called current month, as you can see here. This is done by converting m, which is a number, into a 2-character string using the string filling function setFill. So that's a function over here with an argument equal to 2. So that means that the final month will have 2 characters or 2 numbers. Once the current month has been identified, we use the substitute function, which is this bit in here, which performs the template substitution, returning a new string called current file name, where the field year has been replaced by the value of the current year variable, and the field month has been replaced by the value of the current month value. We then use the glob function over here, to retrieve the corresponding monthly file. So the glob module finds all the path names matching a specified pattern. In our case, this is the current file name pattern, as we just defined above. And bear in mind that the glob function always returns a list of files, so we are only expecting one file per month. So we will slice the array just to keep the first one, as you can see in here. If the file exists, which basically is this instruction in here with an if control sequence, then we use the append method to append the monthly file that we just found to the monthly file list that we defined here. And we also print a message to let us know that the file was found. And if the file doesn't exist, the glob command will return a false value. So this statement after else will be executed, and in this case we will only print a message saying that the file was not found. So this is the hard work basically done, and you can see the the list that we have just created by printing the monthly files and monthly date lists. And with this, actually building the time series is a breeze. It's much easier. So we will initialize the time series to an empty list, as we did with the file list, and then we can loop through the file list monthly files. So we are looping for each file within the monthly files list, opening each one of those files, loading the corresponding chlorophyll variable, extracting the relevant box of data, and finally calculating the monthly mean, the monthly average value, which we will append to the series. So that's the opening, the loading, the mean, and the appending, basically, in these 4 instructions in here. And in here you can see the time series that we have just created by printing the chlorophyll monthly mean time series variable. And once the time series is ready, we can query it for a specific month, as we have done here, for example, for the month of March for 2019. So this is the monthly regional mean for March 2019 over the Celtic Sea. Finally, we can plot the time series and see how the chlorophyll concentration changed from month to month during 19th in the region. The plotting sequences is slightly different from the map plotters that we have used in the past few sections. So here we are introducing 2 new ways of plotting. So we use the plot function to plot continuous lines that you can see from point to point, and then we can use the scatter function to to plot the actual points that make up the plot. So this plot summarizes the average phytoplankton seasonal cycle during 2019. So basically it showcases 2 phytoplankton blooms, one in the spring and one in autumn, and the first one dominates over the second. And similar seasonal variability or variations are present in many other regions. So this technique can be used in any other region that you are interested in. For variables that present the distinct seasonality, the annual cycle can be extracted from the regional signal, and then you have a deseasonalized time series that can be fit it into a linear regression to result in a linear trend. So this kind of study is quite interesting if you're looking at long-time or long-term trends in for a biogeochemical variable. And we will now use these new tools, so the template definition, the loops, and the if-else control sequence, to create a similar type of time series, but instead of doing the monthly time series for the whole year, we will look at the daily time series across March 2019, so we can compare the two of them. So first we define a template for the daily file names, which we call daily template. The variable parts are the year and the month of the day fields. We define the year and the month that we are interested in. As we said, is March 2019. Then we initialize the daily file list variables here for an empty list. And we will also build a twin date function that we will use for plotting. The daily loop will be executed for day values from 1 up to 31. So 31 number of days in the month we're interested in. For each numerical value of the variable d, which will increase in every iteration, we define the equivalent string called day using the same function we used to create the month strings in the previous box. We then use the substitute function. Once that we have the year, the month of the day, we replace those values in the daily template that we have defined at the beginning to obtain the current file name. And as we did with the monthly file names, we use the glob function of the glob module to retrieve the corresponding date file. If the file exists, we use the append method to add it to the list of valid files, which is what we are doing in here. We print a message saying that we are not printing it in here, but we also append the date to the daily dates list. And if the file doesn't exist or the system cannot find it for whatever reason, we print a message saying that it's not possible to retrieve it, the file was not found. Finally, in here you can see the list that we have just created. If you print the daily file list, which we haven't done here, but we did for the monthly time series, it's exactly the same sequence. And with the daily file list for March 2019, then we can create the daily mean time series for this month. Basically, we are doing exactly the same. We are looping through the daily file list, opening the dataset, loading the chlorophyll variable, performing the geographical mean, so this is basically the average value for the whole array, appending that value, so the current chlorophyll mean, appending that to the chlorophyll day mean time series. Unless the chlorophyll mean is not a number, and in that case, basically, we will add not a number to the list. And in here, we can print the final chlorophyll daily mean time series, and also we can compare that with the chlorophyll monthly mean for March 2019 that we obtained for the monthly time series. So as you can see in here, basically we have some gaps on the time series when the mean of the entire region was probably covering cloud. So that's basically, for example, the 5th of March was covering cloud. And finally, we can use the same plot and scatter functions to plot the time series for March 2019. So now each one of these points represent the daily average rather than the monthly average. And again, when you have gaps in your data, that means that the mean was the data array for the region was empty, probably due to cloud cover, and the resulting mean value was not a number. So the time series gives you an idea of the chlorophyll dynamics for March 2019. There's a lot of variability. So in here, for reference, I've plotted in red on the mean value, the mean monthly value for March, but you can see there's a lot of variability above and below that value. So because phytoplankton and chlorophyll concentration as a proxy of phytoplankton respond to quickly to changes in environmental conditions. That means that every time you have a change in temperature, light, nutrients, you will have a jump or an increase or a decrease in chlorophyll. So time series with high temporal resolution allows us to monitor these changes. Just to finish the section, mention that we tend to compute this time series for long times. So basically what I'm showing here is one of the products you can access to the Copernicus Marine catalog, where you can see that we have plotted the daily chlorophyll average concentration for the North Atlantic Ocean for 20 years basically. And then, as I said, we have derived a climatological seasonal cycle, and we have obtained this time series in green, which is the deseasonalized time series, and then we have fitted that to linear regression, you can see here in blue, which gives you an idea of the general trend for the region in the past 20 years. The techniques that we have learned can be applied to almost every value geochemical in the catalog. So in particular, if you want to spend some more time, you can try to produce the chlorophyll, the corresponding anomaly and climatology and time series for the primary production data set that I suggested in part 1 of this exercise, and see how these correlate with the chlorophyll anomalies and time series. I really hope you're enjoying the practical session so far. Well done for reaching the end of part 2, and I will see you again in the third and final exercise. Thank you.